Today's topic, Sn2 reactions. This video requires familiarity with nucleophiles, electrophiles, basicity, and reaction rate concepts. Sn2 reaction is a type of substitution reaction. Substitution means replacing one thing by another. Thus, a nucleophilic substitution reaction means substitution of one nucleophile by another as shown in this example. Just a quick note, today we're talking about substitution reactions at a saturated carbon. These reactions are different than substitution reactions at carbonyl groups. Sn2 stands for substitution, nucleophilic, bimolecular. The bimolecular means that the rate is dependent on the concentration of two species, a second-order reaction as we'll see. Let's look at the reaction of bromobutane with hydroxide as a general mechanism for Sn2 reactions. The nucleophile, which is the hydroxide, attacks the electrophile, which is the carbon bonded to bromine in this case. The nucleophile attacks 180 degrees away from the departing halogen, which leads to the transition state shown. Bromide ion then leaves as the leaving group. So in this reaction, hydroxide has replaced bromide. Thus, important points about Sn2 reactions are as follows. First, there are no intermediate formed, which is why the reaction has a second-order kinetic. The reaction occurs in a single step that involves both the substrate and the nucleophile, and thus there are two molecules in the step whose rate is measured. Second, as the nucleophile comes in one side of the substrate and forms a bond, the leaving group leaves from the other side. This results in an inversion of stereochemistry. Now, let's see what factors affect Sn1 reactions. The first factor is the substrate. Recall that we said the nucleophile attacks on the opposite side of the leaving group. If the substrate is bulky and hindered, it makes bond formation difficult because the carbon atom is shielded from approach of the incoming nucleophile. The difficulty of nucleophilic approach increases as the three substituents bonded to the carbon atom increase in size. The trend is shown here where methyl halides are by far the most reactive substrate and tertiary substrates do not usually undergo Sn2 reactions. Thus, Sn2 reactions occur only at relatively unhindered sites such as methyl halides, primary halides, and a few simply secondary halides. The leaving group is the next factor determining the rate of Sn2 reactions. The best leaving groups are those that best stabilize the negative charge in the transition state. The groups that best stabilize a negative charge are the weak bases. Thus, chloride, bromide, and tosylate make good leaving groups, while strong bases such as hydroxide make poor leaving groups. To carry out an Sn2 reaction with an alcohol, the hydroxide must first be converted into a better leaving group. This can be achieved by protonation, where oxygen gets positively charged. Once the nucleophile attacks, water leaves as the leaving group. Thus, we have converted a bad leaving group, hydroxide in this case, to water, which is a good leaving group. The rate of the reaction also depends on your solvent choice. Let's first define the solvent. A polar protic solvent is a solvent that can hydrogen bond as it contains an OH or NH group, such as methanol and water. A polar aprotic solvent is a solvent which is polar but does not have an OH or NH group and thus cannot hydrogen bond, such as acetonitrile and dimethyl sulfoxide. The protic solvent slows down Sn2 reaction because of solvation. A protic solvent hydrogen bonds to the nucleophile and form a cage around it, and so the nucleophile won't be able to attack effectively. In aprotic solvent, the nucleophile is not caged or masked, so the unsolvated anion has a greater nucleophilicity. Lastly, the rate of reaction also depends on the strength of nucleophile. The reaction is faster with a stronger nucleophile. There are not set-in-stone trends for nucleophilicity, as the exact nucleophilicity depends on the substrate, the solvent, and concentration. But here are a few general trends. First, negatively charged nucleophiles are more reactive than neutral ones. Remember, nucleophilicity is the ability to donate electrons. Thus, if a nucleophile is negatively charged, it will be more willing to share its electrons as it has a higher electron density. Second, Nucleophilicity roughly parallels basicity moving across a row. For example, NH2 negative is a stronger nucleophile compared to fluoride as it is a stronger base. Remember, moving across a row, electronegativity decreases, and thus electrons are less tightly held and are able to form a bond more easily. Lastly, nucleophilicity increases going down a column in polar protic solvent. A protic solvent can hydrogen bond with the nucleophile. Fluoride ion is the strongest hydrogen bond acceptor and is the smallest, while iodide is the weakest hydrogen bond acceptor and the largest. Thus, fluoride will be heavily solvated while iodide will be less solvated, and so its lone pairs will be more free, resulting in higher rates. A polar aprotic solvent, on the other hand, does not hydrogen bond to nucleophiles to a significant extent, meaning that the nucleophiles have greater freedom in solution. Under these conditions, nucleophilicity correlates with basicity, and fluoride ion, being the strongest base, reacts fastest with electrophiles. In conclusion, Sn2 reactions happen in one step. The nucleophile attacks the electrophile while the leaving group leaves, resulting in an inversion of stereochemistry. Sn2 reactions are faster with less steric hindrance, such as in methyl primary and some secondary substrates, weaker bases as leaving groups in polar aprotic solvents using strong nucleophiles. Thank you for watching.